My name is Jiahao Wei. I'm a PhD from University College Dublin. The name of my presentation today is Modeling of a Baffled Horizontal Subsurface Flow Constructed Wetland, Optimizing the Hydraulic Performance. I'll use this?
Yes, exactly.
My presentation will be divided into these 4 parts. Okay, sorry. The key objectives of my work can be concluded in these 2 points. The first one is to obtain the flow field of the constructed wetland. And the second one is to assess the hydraulic performance under different baffle settings. First, let's start with some background knowledge. Constructed wetland is a commonly used green technology for wastewater treatment. And generally, it can be classified into 2 main types according to hydrology: surface flow and subsurface flow. And subsurface flow can be further divided according to horizontal flow and vertical flow. The picture on the right-hand side shows the type of the constructed wetland I simulated. Which is a horizontal subsurface flow. It consists of plant and substrate. The substrate can be gravel, sand, serum site, and so on. Overall, it's porous structure. The water flow into the system, and when it flow out, it can be purified because of the biofilm on the carried on the substrate. However, an unfavorable hydraulic performance, such as short circuiting, back mixing, can significantly affect the treatment efficiency of the constructed wetland. So it's very important to make sure the system has a good hydraulic performance. Let me explain in more detail. Constructed wetland requires a certain amount of time for the wastewater to stay inside the system before it can be purified. This time should not be too long or too short. But in real life, because of the short circuiting or other poor hydraulic conditions, the water particle spend different time in the system. This is called residence time distribution. If we do a tracer study for a tank, and we presume the tank is of ideal hydraulic condition, we inject some certain amount of tracer at the inlet. After some time, we will get the concentration of the tracer at the outlet, like the right-hand side, the blue stripe, like that. But in real life, without ideal hydraulic conditions, the RTD curves shapes would be like that in the middle. Some will stay longer, some will stay very short time. Besides, all the indexes to evaluate the hydraulic performance are derived from RTD functions. The 2 most important indexes are hydraulic efficiency and dimensionless variance. This picture shows the geometry I simulated. You can see the basic structure of it, the inlet, outlet, baffle, and the dimensions. The whole domain is filled with porous media. And since the the geometry is quite simple, so the mesh quality is pretty good. And the right-hand side shows the main approach to my study. Firstly, I used the InterFOAM to obtain the velocity field. As you know, InterFOAM is a two-phase solver, so this step can provide the information about the water surface precision. And then I use the scalar transport form, which is a solver for resolving the transport equation for passive scalar T. This step actually simulates the tracer movements through the tank. And then I simply monitor the scalar T at the outlet in ParaView to obtain the RTD curves. Ultimately, all the indicators can be calculated based on RTD curves, and then the hydraulic performance can be evaluated. This is the basic porous media theory in my study. Porous media is modeled by attenuating the time derivative and by adding a source term to the Navier-Stokes equations. In my case, I use FE options to add Darcy-Fortimo equations as a source term. And I use these two empirical formulas to calculate the coefficients C1 and C2. In OpenFOAM, we always define these two coefficients in FV options. These two tables show the main setup for my case. The porosity is 40%, and average particle size is 5 millimeter, which should be converted to the values for D in FV options. And the boundary conditions for inlet U, as said, the flow rate inlet velocity 0.006 meters cube per hour. So the nominal residence time is 28.8 hours, which means that when the water flow into the system, each single particle theoretically should be stay in the tank for this long, 28.8 hours. And I said the T value for one. Generally, there are two most used methods for injecting the tracer, which is pulse input and step input. In this case, the value for T was kept constant during the simulation, so it can be considered as a step input. This table shows the combination of the parameters, the baffled parameters the combination of baffled parameters in my simulation. In my study, I mainly tested two baffled parameters, which is baffle length and the baffle number of baffles. In these cases, the flow rate and inlet-outlet configuration and porosity were kept constant. So there are 30 scenarios in total, and I also test one case without baffle inside. Here are the results for the flow field. The flow behavior is quite important for the constructed wetland because it has a huge impact for the biological processes within the constructed wetlands. Since the contaminants movement and residence time is determined by the velocity field. these 5 figures, they all have the same baffle numbers, but the baffle length are different, ranging from 0.4 to 0.58 meters. And you can see they all have the very similar, the same relative high velocity area near the inlet, because due to the same inlet setup. And they also have the same high velocity zone at the end of the baffle, the inner band there, especially for the case C4 and C5. It's simply because the smaller cross-sectional area caused by the longer baffle. And the velocity for the dark blue area is 0 or extremely low, representing the dead space in the reactor. We can see most of the dead space concentrated at the corner in the reactors. This figure shows the result from another angle. These four, they have the same baffle length but different baffle numbers. The baffle length are all 0.5 meters, and baffle mount from 1 to 11. It can be clearly see that the cross-sectional velocity noticeably increased as the baffle amount increased. So in conclusion, the baffle amount has a significant effect on the cross-sectional velocity, and is conducive to reducing the dead space. And based on the result from CFD and by monitoring the T value from the outlet, we can get the RTD curves like this. The shape of the RTD showed in the figure 4 is exactly what I expected before. The concentration rapidly grow to the maximum, and then gradually decrease to the initial value. And if you look at the figure A and B, when the baffle length is 0.4 and 0.45 meters, as the baffle amount increase, the RTD curves almost keep unchanged. And there is a slight change in the case the baffle length is 0.5. But when the baffle length is 0.55 and 0.58, the RTD curves change a lot. It becomes taller and narrower, which means that it's closer to a more ideal plug flow condition. And this is also from another angle. They all have the same baffle amount, but the different baffle length. You can see when the baffle amount is 1, the RTD curves doesn't change. And when and there's a slight change in the case of 3 baffles. And so what we can get from here is the two parameters here, baffle length and the number of baffles, they all have to reach the certain amount. Then we can get a good hydraulic performance. I mean, if one parameter is small and we increase another parameter, the RTD curves doesn't change. It will not significantly change the RTD curves. And as I mentioned before, there are some indicators to evaluate the hydraulic performance of constructed wetland, the hydraulic efficiency and the variance. We can see from the picture, there's the picture A shows a gradually rising trend, except the case with the 0.4 meters baffle. And however, you can see overextension, the baffle length or the baffle amount cannot benefit the hydraulic performance, hydraulic efficiency. And for the right-hand side picture, the variance, this indicator describes the gap between the real flow pattern and the ideal flow pattern. So if the variance is 0, it's the ideal plug flow condition. So this indicator, the smaller, the better. You can see the similar trend is shown in the right figure. Overextension, the baffle length and the number of baffles cannot significantly reduce the dimensionless variance. This is the main conclusions of my research. First is baffles are effective and reliable devices that can be used significantly reduce short-circuiting and dispersion and keep the dead zones to a minimum. The second is when the baffle length is greater than 0.5 meters, increasing the number of baffles has a significant positive effect on the hydraulic performance. Besides, when the number of baffles is greater than 3, increasing the baffle length will improve the hydraulic efficiency significantly. The last one is the best combination of the two parameters is 0.55 meters baffle length and 7 baffles. In addition, excessive extension of the baffle and increase in the number of baffles do not significantly improve the hydraulic efficiency and reduce the dimensionless variance. Thank you for your attention.
Thank you, Jiahao, for the nice presentation. We are now open for questions from the audience in person. Are there any questions? Please. Could you
have you considered using the mid-age formulation of U? So this is a steady-state formulation that computes the residence time distribution.
Sorry, could you repeat your question?
Sorry. Using the min-age formulation of
yeah.
U. This is a steady-state formulation that is equivalent to
steady-state.
an unsteady computation of the residence time, and it just adds some equations to the Navier-Stokes equations.
Yeah.
So convection diffusion equations for moments of age, and then you get the first moment is, for instance, the residence time. So you have a local residence time distribution.
Yeah.
Have you tested this or not?
This is the steady state. I didn't consider the. I haven't considered the unsteady state conditions so far. So I plan to test the effect of flow rate later when the flow rate change during a certain amount of time, and we can see the effect to the on the residence time curves.
Any further questions?
Yeah, what is the purpose of having high variance on your last results? So I get why the figure on the left, kind of hydraulic efficiency, I get why that needs to be high. But what's the role of the variance?
The role of the
variance.
variance. The variance indicates the dispersion and mixing condition in the tank. So the variance, if the variance is bigger, then the back mixing and is there are more back mixing in the tank. Yeah.
I'll quickly check if there are any further questions in the chat. I do not see. So I will take the privilege to ask you a question. So you showed the velocity plots for different configurations, right? So my question is that I just wanted to confirm, in all the possible configuration that you have studied, the flow field is steady.
The flow field is steady. Yeah.
Yeah. So did you interpret it something that if you observe the vorticity field, something whether they have any role to play in the hydraulic efficiency or any physical insight from the flow field? Did you?
Sorry, I didn't follow your question.
Did you interpret some physical insights from the flow field, that how the flow field play a role in moderating the hydraulic efficiency? So I will rephrase the question. The velocity plots that you showed, can you go back to that slide? So
yeah. What
can we infer from them that in terms of what role the flow
field, what's the role of flow field?
Yeah.
The scalar transport form requires a given velocity field to calculate the transport equation. So we need that velocity field.
Yes, but can you go to the slide?
Okay,
Actually,
okay.
my question was slightly different. Yeah, here, let's say, so if I consider this analogically as a vorticity field, this is a velocity field. So the strength of this flow velocity, as you told, like, did you study if they have any role in mixing or any other physical phenomena that you are studying?
The velocity field can just let us know where is the low velocity area, where is the relative high velocity area.
All right. Yeah. Okay. So if there are no further questions, let's thank the speaker again.